Okay, thank you very much. Again, thanks very much for everyone joining in the webinar. And I enjoyed putting this together. It's kind of a slides from several presentations I've done the last couple years. And so hopefully you can gain some of the knowledge that I gained doing this for the last 30 years. So anyway, with that, we'll start the program. And just to let you know, I am doing this from my home office, so hopefully everything will go well and from that standpoint. So we'll just chug away and see what happens. Like I said, to graduate from Nebraska, some of this does repeat, Iowa State in '87, and worked for the midwives firm and then started my own LLC. So that's kind of was in the background, but everyone kind of makes fun of me because I got a lot of acronyms after my name, and a lot of that stuff is just part of my goal in engineering was just to keep current in what's going on in the profession. So, and with that, unfortunately, comes a few titles. I want a little bit more information on myself, so you got a little bit of background on myself. And actually, just this month, I got a Environmental Champion Award. And kind of one of the things I like to do as an engineer is also do other things besides engineering. So that was a pretty proud moment to get that award, to be recognized for that. I have also been a guest lecturer at UNL and UNO classes on green infrastructure. So I had an opportunity to talk to mostly non-engineers. So that's kind of always interesting as an engineer. And then a lot of this presentation at the end is from a presentation I did out in Denver in November, where I was talking about maintenance. And again, it was really good to go see other people doing maintenance and how that's all done in the LID green infrastructure world. And just a little more background that actually when I was started my career in Minnesota, I was on the Water Resources Committee at that time, and that's when green infrastructure and all the good stuff started in Minnesota. Was there kind of on the cutting edge, and then now I'm a board member of the Nebraska floodplain. So here's kind of the agenda, what we're going to go through today. I'll go through some background, some challenges of green infrastructure and LID, some modeling foundations, because I think it's kind of important we talk about what we do when we model, not just the modeling and the maintenance part of it. How you specifically model green infrastructure, some key points. It is somewhat unique. I'm going to briefly describe 3 models, and more or less, I kind of switched a little bit in the presentation. I want to focus more on real world stuff and not so much on specifics of the model. So I'll touch on those a little bit. Each of them kind of are unique. And then briefly again, I'm going to talk a little bit about modeling the BMPs in the Iowa Stormwater Manual and just more of a concept. And then I think the most important thing here is that we'll talk about maintenance modeling case study, Spring Lake Park in Omaha. So I think it's important to kind of see how the modeling can actually, excuse me, can actually be used. So we'll dive into this. Excuse me. What I wanted to put out this is a point that the other person I work with a lot is a landscape architect, and he kind of put this comment. I said, so when did rainwater, a resource, become a stormwater a nuisance? And again, I think as we talk about green infrastructure and LID, we really have to treat rain like a gift rather than dispose of it as trash. And I think that just to make a point, actually John Royster and Ryan Bentley will actually be doing a future webinar in this series on September 11th. So keep that in mind and hopefully put that on your calendars. Another quote is that I really liked, and finally, we still need to remember that it is not solely wisely developed or green urban infrastructure, but human behavior which ultimately determines our sustainability. So kind of my quote is, if there's no people, there's no problem. So again, when we move forward and we talk about green infrastructure and LID, it really is kind of how we interact with the environment. So let's talk a little bit about the challenges of green infrastructure and LID. One of the challenges of the GI and BMP design, there are really many perspectives of what is ultimately a great design. And part of what I did last year in 2017, I kind of did a stormwater tour here in the Midwest. And one of them was actually in Iowa in Chloroville last summer, and got to see a lot of new stuff on the porous pavers and all kinds of really neat stuff. Then Omaha has an annual green infrastructure tour, and this year they had a green roof, so it's kind of, again, something a little bit unique and different to see. And then, like I said, in November, I was out in Colorado at the maintenance conference for LID. And what was kind of interesting, that the last thing we saw was actually a facility for maintenance where they take their street sweepings and they store them and they let it get dewatered, because what they found out, the cost of water when you landfill it was an expense they didn't want to bear. So again, a lot of times as designers and modelers, we kind of look at the front end, but we don't look at the back end. So that was really interesting as part of that tour to see the maintenance part of it. So I'm going to kind of go through these different perspectives. So again, here's a landscape architect perspective. Well, I found this in 184 plants, and as an engineer, I see something like this, or maybe even as landowner, and I'm kind of in a panic mode. But again, as a landscape architect, their perspective is, wow, this is really neat, a whole lot of plants. That's what it's all about. Now, if you take a soil scientist perspective in green infrastructure LID, it's kind of all about, well, what can the soils do? So here's a case study in Minnesota where they went into a green infrastructure and they just sampled the heck out of it, trying to make sure they understand what the soils are going to do. And then, of course, there's the engineer's perspectives. And this is kind of what it looks like. Hey, dig a hole, put some plastic over it, and by gosh, it's working great. And then, of course, now that we are in the green environment, there's kind of the green infrastructure perspective. And we plant grass around it, but like all good engineers, we have to throw some riprap on it. So again, each of us kind of has our perspective when we come into these. So I think the key is, as we move forward with the modeling, we really don't want this sole ownership. So let's move ahead on the agenda and let's kind of talk about what is that modeling foundation and how do all these disciplines fit into that. But since today's focus is on water resources, and as water resource engineer, I kind of want to do a little history lesson so we kind of know a little bit about where this all came from. And so I'm going to start with a quiz. What year was this written? The increasing focus on water quality and urban water resources has as a corollary the identification and application of engineering techniques that will preserve and enhance the natural features of a locale and maximize economic environmental benefit. Improvement of the effectiveness of natural systems rather than replacing, downgrading, or ignoring them is an object of what year engineering standards? So was it 1968, 1979, 1994, 2007, or made this up? There's no way an engineering document would ever say that. Well, the answer is 1979. So that's almost 40 years ago. There was an awareness of the link between engineering and how we go about green infrastructure and LID. We just didn't call it that at that time. And this is actually from the Design of Urban Highway Drainage, state-of-the-art, August 1979. A little bit more history on myself. This is actually the hydrology book that I used when I was in college at Lincoln. And again, it's the definition of hydrology. Estimation of some aspect of the quantity of water available is the prime importance in all water resources engineering. The analysis is basic to the planning, design, and operation of water resources systems. So again, this is 1975, and we're kind of looking at the importance of the complete process. What I kind of highlight in this whole process is really, when you think about it, a lot of times we're really focused on the design. That's where we get simple equations and stuff to make our life easier. But I think the key is when we're starting to look at green infrastructure and LID is that kind of that plan extent. So from the standpoint of green infrastructure, I think we really need to start with a common sense approach in that planning stage. And I bet most of us in this audience, if we thought about it, about 90% of your final design in green infrastructure and LID is in that planning stage. You could probably do most of your designs on the back of a napkin if you wanted to. So that's kind of the thought process. If you think about it first, then what you do with the design is you're really looking at that to prove it will work in the modeling stage. So again, modeling now has a purpose, which is basic look at what you think will make sense. And then the operation becomes the maintenance and resiliency of the project. And again, we tweak it a little bit. We still have our common sense planning approach, but then the design becomes modeling for proof and then function. So we want to say not only how that it will work, but how will it function over different events and over time. And that helps us a lot with that end product maintenance and resiliency. And again, I had to kind of laugh when I saw my book and pulled it off the shelf. But again, it's hydrology for engineers and planners. So again, even in 1975, the thought was we had to continue this kind of multidiscipline approach to this of hydrology and water resources. And can't go away without doing a little Iowa State. And this is actually from my thesis. An increase, and this is from Dr. Ron Rossmiller, who was my professor at the time. An increased awareness of the adverse effects of conveyance approach, pipes and concrete swales, in other words, has brought about a new philosophy toward urban drainage, labeled storage approach, that used in areas' natural landscape to retain the runoff where it first falls. Again, this was in 1987, over 30 years ago, and I didn't know it at the time, but I was actually doing LID stuff in my master's thesis as I was working in the EPA swim model at the time, and it did show the value of how storage was part of an LID process. And last but not least, one little history thing, which I think is of value, is that in 1991, I worked on a project in which we actually started using prairie restoration around a pond that we built as a detention area. And this is actually the brochure from 1991, Prairie Restoration. So why was this important? Well, after construction, 1991, a few years later, it looks great. It's a nice wetland area. So I guess from a design and environmental standpoint, it's really a good deal. But I just went out and visited again in October of 2017, which all of a sudden that green infrastructure project with prairie restoration now was full of tall grasses, weeds, brush, and everything else. So again, when we're looking at the modeling and the maintenance, it's kind of, we really have to, will it be maintained or not be maintained? And then the value potentially of the modeling is, well, what happens if the maintenance falls apart? And again, this is what prairie grass can look like 27 years later if you really don't maintain it. And again, from a modeling standpoint, 27 years ago, we didn't think that they were basically not going to maintain the project and all of a sudden see 30-foot high trees where there was supposed to be prairie grass. So again, kind of that concept of modeling is looking not only currently, but in the future. And real quick, engineering, this quote from Durham Museum is the art of science applying scientific knowledge to practical problems. So again, I think green infrastructure and LID is really about that process, and how we'll talk about later is how the modeling fits into that practical solutions. And again, I'll fly through this, but again, the balanced design, modeling is really part of that multidisciplinary design. We'll talk about that. And it really gives you that, what you want is that long lasting project with limited or no maintenance. So again, let's go back to overcoming sole ownerships. What I kind of like to use is, I call it my simple soil column, and we can kind of think of green infrastructure kind of fits into this, where we have the surface depression in our green infrastructure structure, and that's kind of the hydrology engineer. A lot of times regulatory requirements tell us, well, how much water is getting there and what do we need to do with it. Then we kind of have the growth zone, that's where the plants go, and brings in our landscape architect. But again, the cross knowledge of using the modeling is great. And then I kind of call this the infiltration zone, the multidiscipline zone, because really we need to know the soils, we need to know what will grow there, we also need to know how it's wet. So we kind of all play into the role. And a lot of times in the groundwaters, the soil scientists will tell us, hey, what's going to actually get out of our green infrastructure and go into the soils. Again, here's kind of the real world. The hydrology helps with the rain and how it gets there, with beautiful plants and the landscape architect. Again, we kind of study it, and then the soil science. But again, want to emphasize the fact that this is a multidiscipline for successful green infrastructure. And then as we go through today, it's kind of that role of modeling in that multidisciplined world. Oops, apologize for that. So let's go into modeling green infrastructure. Will be the next thing on the agenda. So we'll kind of talk about the basics. Again, from a hydrology and hydraulic basics, there's lots of models and methods available. So when you're out there searching for the methods or what will work best for you, there are plenty to do out there to work with. And then understanding the components of hydrology and hydraulics models make you a better designer and gives you a better understanding of the value of modeling and when to use it. So again, I've had an opportunity to work with landscape architects and different people. And again, I think the more I learn about plants and how they work and the infiltration components, and the more they learn about how I do my engineering and modeling, it just makes for a better project. And we'll really show you how that worked at this Omaha case study that I'm going to show at the end. And then finally, I'm going to use NRCS to kind of discuss the basics, because I really want to go to the basics of the modeling, because if you understand the basics, you can understand how to use the actual models and how they work. So again, NRC, it just works well. It's consistent with the Iowa Stormwater Manual, and plus it's pretty easy to understand. And again, what are the basics? Well, first of all, almost always volume of runoff is a key factor when we're looking at mostly for a lot of times for the water quality and the small events. So we have to kind of understand, well, what impacts the water quality or the volume of runoff when we're looking at the modeling, and also when we're looking at LID, what we can do before we even model. So again, we're going to get some kind of rainfall or precipitation amount that's going to come out of the sky, and it's going to head towards us. Then we're going to have an initial abstraction, which is some of the losses. So that's the stuff that ends up on the plants or in the little depressions in the parking lots that just literally sits there until it the sun, for the most part, evaporates a lot of it, or the plants uptake it. And then infiltration is the stuff that disappears into the soils from the standpoint of after it rains. And then finally, after all that stuff is gone, we get a runoff. And why NRCS uses Q for volume runoff, they do, but it's always kind of confusing for a lot of people when they look at this. And again, we're going to look at the other components. With volume as one side, but as we get into maintenance and design on the higher end storms, flow becomes a key design factor. So what affects that? We still have our losses like we talked about, the initial abstraction and the infiltration. But now we got another component we're going to add, which is time of concentration. So again, how long does it take that water to flow from the furthest end of the watershed to the end? And then the final piece is really, when we're doing from a modeling perspective, we have to decide how much rain we're going to get. Then we have to decide how it's going to be distributed. A lot of times you can, and many of you out there said that, well, if I get a 2-inch rain that happens over 24 hours, that's a lot different than a 2-inch rain that happens in 15 minutes. And then again, from a modeling perspective, that's something you have to consider when you're looking at flow. So let's talk a little bit about how volume and runoff works in the GI-LID modeling world. So this is kind of my design event philosophy in layman terms, and I kind of, as a lot of the discussions at conferences, whether it's the floodplain conference or stormwater, a lot of people are talking about, why do we call things events like a 2-year, 10-year, 100-year, and you hear that on the newscasts and all this, and I think a lot of people get the perception that, oh, like we talk about, well, I had a 100-year storm last year, I guess I won't have one this year, because there really is no understanding of exactly that. It's just a probability. So I kind of thought about this, and I kind of came up more with these, what I call layman's terms, and You can probably think of your own too also. So there's the frequent events. So that's the one that happens a lot of times throughout the summer and in the fall and the spring and whenever it's raining. And again, usually that's used for volume control. And in our world, when we're looking at the water quality components of green infrastructure and LID, that's really 90%, a lot of times is that target that all rainfalls less than 90% are considered frequent. Then we have kind of what I call stability event, and that basically is, well, once the stuff leaves the system, there's a point where it starts to degrade channels and erodes backyards and stuff, and those kind of events. And so again, typically that's kind of a 2-year, but you also hear in bridge design, bank-to-bank flows, and there's lots of terms for it, but it's kind of that point at where your drainage system begins to fail. And then there's the nuisance event, and then that's the where you get the limited complaints, maximum water people will tolerate. So typically that's kind of, we always design, used to be for a 5-year in streets and storm pipes, and now it's kind of bumped up to 10, and now I think some people wonder if that's enough. But I think when you're looking at nuisance event, it's basically asking, saying, well, how much can you tolerate before you feel this is not going to work? And again, nuisance can also be how much water in your backyard, how much in your gutters, you know, in your streets. So again, all of that is part of the nuisance discussion. And you can ask people, if you ask 10 different people, I bet each of them have a little bit different perspective. And also sometimes a nuisance event might be your political event from the standpoint of, at what point do I need to begin stormwater improvements or begin looking at LID and green infrastructure to reduce flooding? And then there is the flood event, but I kind of define the flood event as the major damage. So again, when we're looking at LID and green infrastructure, there's a point where flooding is going to cause lots of problems and cost. And you can look at it from a resiliency standpoint of pure damage. Now, obviously, a flood event in a hospital is probably not the same as a ball field, which again is not the same as someplace in an open prairie or where nothing's going to happen. So again, if you look at it from a flood event that you don't tie it to a recurrence interval, like a 100-year or a 500-year, you can say, well, geez, a flood event in this location where people aren't is a lot different than a flood event where people are, and that may change the way you look at it. And again, the last one is always that act of God event. And I kind of threw this out here because I wonder sometimes if we've kind of can't use that as a design event. But the good thing about in a modeling, as we'll talk about later, we can actually look at relatively large events and see if our system will work. So that's a great thing about modeling. You may not ever call it an act of God event, but you can actually go through the process and say, well, what is the worst case scenario? Probable maximum precipitation or whatever the situation is. Or better yet, I kind of really like to use the term resiliency, which basically means at what point can your system, and then sometimes it's the individuals, bounce back from a wide variety of rainfall impacts. So it's really the easy to fix after you have some kind of event. And again, LID, you really have to deal with all these events. So really quick, this is not anything new from different perspectives. So I thought, let's kind of look at how Iowa Storm Planner looks at. They call it the unified sizing criteria. And I'm sure many are familiar with that. But again, water quality volume, a recharge volume, channel protection storage volume, overbank flood protection, and extreme flood protection. Very similar to kind of the layman terms that I put together. But again, it's looking at that multi-event criteria, and that's really what's the power of the LID green infrastructure modeling. And then I thought I threw in Denver, Colorado, and they call it the full spectrum detention. And again, a very similar, different terminology. First, there's a focus on controlling peak discharge over a full spectrum of runoff events from small frequent storms to the 100-year event. Now, flood, they obviously cap it at the 100-year flood, but again, they're saying you have to look at all these. And then the second thing is the full spectrum detention. Facilities produce outflow hydrographs that, other than small release rates of accessor, replicate the shape of the pre-developed hydrographs. So again, that goes back to that concept of low impact development. Can we design things in the watershed or through the green infrastructure that will allow us to reproduce what was out there before we started in living in these areas. And then finally, full spectrum detention modeling, and I emphasize modeling, has been shown to reduce urban runoff peaks to levels similar to pre-developed conditions over an entire watershed, even with multiple independent detention facilities. Again, modeling is a very powerful tool when you're looking at LID and you're comparing things before and after. So let's talk a little bit more about the basics. So starting with precipitation. And again, the challenge with precipitation is, well, what do you pick? You can pick a design event for water quality like the 1.25, the 2-year, 5-year, 100-year, 25-year. We talked about PMP. So again, it becomes lots of choices, and depending on how you go about approaching this, it can take a lot of time and energy. So you might just say, well, I'm only going to look at 1 or 2 of these and call it good. Well, from a maintenance standpoint, that may not be the best idea. And then again, how that rainfall is distributed always becomes a key component in the design. And historically, the type 2 and how for some of the old school ones, IDF curves with the rational method. But another one, the nice thing about like a SWIM XP or the EPA SWIM model is you can do continuous simulation. So if you had an event that caused problems, or you'd like to run a whole summer worth of rainfall and see how your BMPA works, you have that opportunity with continuous simulation. And then finally, where did I get my rainfall amounts from? Historically, it's technical paper 40, and the new is Atlas 14. So again, there's lots of things that go into rainfall and how it falls. So if your time and money is a value, it's kind of like there's lots of choices. So if you pick the wrong one, it may be a problem with your maintenance program. But with a nice thing about I'll show with the model is you can do lots of things really fast. And then I can't leave without mentioning climate change. Again, it's one thing to talk about it, and from the standpoint of what do I do about it as an individual, as a government, but as the engineers and landscape architects and those working in the green infrastructure LID world, we have to potentially design for what the future looks like. Kind of like I said, I didn't know what the future is going to look like on my project in 1991. But the nice thing about modeling is we can kind of look and say, well, what happens if maybe it's a little more rain or it's a little more intense? And will my green infrastructure LID survive that? So a few key points. Again, mention this over and over. Use the power of the model. Once you get your model set up, you can run several events, and from rainfall to distributions. That's really the power of it. Then you can begin to look at the what ifs and make sure that your system is maintained. And then you can run, like I said, frequent events, water quality, design events, flood events, and you can really even check the climate change. And assume comparisons are relative but not absolute. I've had a coworker once say that, and I also know there's a webinar on hydrology being voodoo. So again, we're not dealing with an exact science here. We're really working on, from the standpoint of hopefully a pretty good guess. They've also said hydrology is more of an art than a science. So again, when you're looking at this stuff, you can't say, oh, geez, if it rains this much, the water's going to be this deep. What we want to really look at is what are the potential impacts, because even whatever design event you use or think it is, it will never probably ever happen in the real world. So the real goal is to compare pre-LID with LIDs and same storm distributions and rainfall. So you look at some basic criteria, you compare it and say, well, if I do this, this is the impact. So for example, if you change something and the impact is a half a foot, that's probably significant. But if the change something and the change is 1/100th of a foot, you go, well, it probably isn't worth it. So again, it's kind of a relative discussion. And the other thing is you really want to, doing the precipitation, the modeling, you're looking for trends. So in other words, is it getting worse or what's going to happen? And again, I want to point this out, and hopefully a lot of you know this, a 100-year rainfall does not produce a 100-year runoff. And that applies to all rainfall events. Too many times in the small LID green infrastructure world, we do a lot smaller events, and we don't really have stream gauges and all this other high level stuff where the original 100-year came from. So we have to use the rainfall events. And a lot of people say, well, geez, it rained 2 inches and it didn't flood me last time, and now it rained at 1 inch and I got flooded. Well, how's that a 100-year event? So again, keep in mind that when we're doing this green infrastructure, that the rainfall doesn't actually mean a runoff. So again, that just adds another complexity and variability of what we do here in the modeling world. So I want to talk a little bit about some of these parameters and how they affect more or less in the LID world, which then helps with the maintenance in the end. So again, initial abstraction, that's kind of the stuff that doesn't go into the soils and kind of sits there and leaves. And I kind of had to laugh. I need a little picture through on this, but you know, what's when it rains on tulips, how much gets captured in the little tulips of it? So again, that's initial abstraction. It goes into the tulips and sits there and never really leaves until the plants take it up or the moisture leaves into the atmosphere. So NRCS defines IA as the initial abstraction consists mainly of interception, infiltration during early parts of the storm, and surface depression storage. And you know, again, here's just some kind of thoughts of bushes and roads and trees, and what's the pavement, a mowed yard, what's in the pavement in your house, in your front yard, maybe the tall grasses, and again, some more trees and a road. So what's the significance of the initial abstraction when we're looking at this? Well, land cover impacts the initial abstraction. That's a key component. So if we use the NRCS, which I like to use, if your land cover is all woods, a B soil, it takes 1.65 inches of rainfall before deep soil infiltration begins and runoff might start. So in other words, if your green infrastructure water quality design is 1.25 inches and your whole area is woods, then basically you don't need any green infrastructure. You already have an LID in place and it's great. So, but if you take it to the other extreme, if it's paved, it only takes 0.04 inches of rainfall. And since concrete is really a porous soil, runoff is almost immediately. So you can now begin to see how you can use kind of that common sense up front approach and justify it through the initial abstraction discussion. Say, well, geez, if I got a lot of woods and in an area and I need to do some development, the more I can save or reestablish that, that's going to help reduce my green infrastructure downstream. So again, that's the LID. So you can kind of play a lot of thought games and process games through that. And it's from the initial abstraction perspective. And here again, here's some key points: complete vegetation inventory. So again, this is more the LID concept, is that look up in the watershed and say, okay, let's look at our vegetation. Let's keep the good stuff if we can. Let's replace it with stuff that's going to make sure that we capture as much water up in the watershed. And again, from a small event, there's a pretty big impact of working on the initial abstraction. But as you get the large rainfall and storm events, this isn't a great benefit to reduce the, say, the 100-year, because at that point, so it's just not that big of a piece. So keep that in mind, but it's a good place to start. And I think it's really easy to understand initial abstraction. And then another nice thing is you can kind of use some common sense spreadsheet hydrology up front to kind of look at, well, if I keep this much woods or I don't, or I flip this or I convert this to grass, you can kind of see the impact of from that perspective. And again, from a maintenance and resiliency standpoint, if I don't get there, don't have to deal with it. So again, watershed approach, we don't have to work at the end of the pipe or end of the watershed. Real quick, let's talk a little bit about infiltration. Again, that's the piece here and from that perspective in the NRCS world. And again, we're talking about models, and Heck HMS is one of the models to just briefly touch on, but they have 10 different methods of dealing with infiltration. The EPA SWIM model has 3, and again, if you're doing really anything with TR20 and the HydroCAD, there's basically one method of infiltration. So it kind of guides you towards, if infiltration is a really big piece of your design or your watershed analysis, it's a great way to, that might direct which model you pick. And again, just to emphasize the value of infiltration and how it impacts what you do. Again, these are kind of the soil groups. A being the sandy soils, you can see a very high infiltration rate, down to the C's, which are the clays, and then D's, which really nothing gets into the soils and it all runs off almost like concrete. So for NRCS curve numbers, how much rain will it need to fall until runoff occurs off a grass area for various soil groups? So here it is again, that same concept. Now we've taken the initial abstraction concept, expanded to the infiltration concept. So if we have a grass area and our whole watershed is grass, and our design water quality rainfall is 1.25 inches, we can kind of see that, hey, if we keep it in grass and A and a B soil, got pretty good soils, we really don't need a green infrastructure maybe, or we can use the land use for that. And then obviously as you get into the C's and D's, then we need to begin to decide, hey, if our criteria is 1.25 inches or whatever, we may have to do something. But I'd like to point out at the bottom there's that impervious 98, which basically means you get impervious, you're doing green infrastructure, or you're trying to mitigate it through other methods in the LID. So again, this is great because you can do some spreadsheet stuff and do some what ifs. But I want to take a little detour here because I wish it was that easy from the standpoint of, hey, let's just look at land use and call it quits. So I'm going to kind of take a little tour here. So let's kind of look at an NRCS CN values over time, and we'll kind of focus on that. So kind of looked up, most of Iowa was prairie grass before people started settling it. So if we kind of look at the B soils, it was kind of probably a 58 from that standpoint. Then we start to pasture and put animals on it, not quite so good. Then the values begin to go up. We, like almost all Iowa, are now in row crops. And again, the curve number is going up to 75, this case in the B soils. And then we say, hey, let's get rid of those row crops and put in 3rd-acre residential. And if we kind of note, it's kind of interesting, the row crops was 75 and the 1/3-acre residential is 72. So does that mean that I don't have to do anything because it's actually better to put houses in than it is in row crops? Well, obviously that is not the case. So how does that fit into the modeling world? Because if I look at it from a full watershed standpoint, I would actually run the model and I'd say, oh, existing conditions 75, future conditions 72, we don't have to do anything. Well, Nelly, as like say on a so kind of an example on a 3rd-acre residential, NRCS methodology was designed for larger storm events. So for LID GI events, need to break the watershed into direct impervious and indirect impervious plus pervious to better stand the impact of BMP on a watershed. So kind of, and I'll go through this a little bit more detail, how that kind of works. But basically what you end up doing when you're incorporating the green infrastructure and LID into your design, you have to kind of take your model and like I said, you break the watershed into direct and indirect. Now, from a pure hydrologist standpoint, they might say, well, that's kind of crazy. That doesn't make sense. But what's interesting is when the water quality models came out, especially it's called Det Pond out of Wisconsin 20 some years ago, that's basically what they did, because they found out that for small rainfall events, if you don't look at the direct impervious surfaces running off, you don't get any runoff. So that was kind of the key. And again, here's the imperviousness in the model, and then you have the direct impervious. So you have indirect and direct. But I also want to note that some models, such as SWIM and HEC HMS, have this concept built right into the model. So you don't have to necessarily run 2 watershed models and add the hydrographs together. You can input the direct and indirect impervious areas or a percentage as part of the data required for the model. So again, there was that recognition that, hey, when you're looking at small events, especially in urban environment, you can't always just use that simple TR55, TR20 mentality, and you have to kind of cheat a little bit to make it work. But I'll show in the case example how well that did work. And again, here's how it works on paper. So there's two options for third acre residential. This one I just talked about, lump them all together. And here's how it kind of works. If you say, okay, I'm going to take of that 30% impervious, 19% flows immediately into my downstream system. So obviously all the curb numbers are very high, and you're going to get almost 100% runoff. But you also should adjust the time of concentration, because obviously if it's on paved surface, it's going to go a lot faster. And then you take the pervious and the indirect impervious and you combine that, get a weighted curb number. And again, you can see where there's a 98, but where it used to be 72 for third acre, now you're kind of looking at a 66. So what you're basically doing is taking 100% runoff. But what you'll find out is if you actually do the analysis, as you get to the larger storms, the 10s and plus 10-year, they basically begin to give you essentially the same results. And we'll go back on the kind of summarize the volume. So results vary depending on many factors, can be easily identified, soils maps, land use maps, vegetation cover. Again, if you're looking at how infiltration is impacted, and again, spreadsheets are a great tool if you're looking in that upfront stuff to kind of get an idea of how I should convert land or keep land or how that works. And again, like I talked about, we're looking for trends, not absolutes. And again, use non-engineered tools like the general equations, spreadsheets to get a good idea of the impact of a wide variety of LID land use impacts. And it kind of goes back to my philosophy, that common sense up front in the planning stage. What can I do that's simple to get me on the right track and convince myself what I'm doing before I start diving into models and spitting out results? And let's talk a little bit about the impact then of all this on discharge rates, which is a little bit different. Of course, soils and land use have an impact, so methods for volume reduction also work for peak reduction. But other factors, like I talked about, is your choice of rainfall distribution and your time of concentration. In other words, how the water travels through the watershed and the slope. So here's just kind of some time of concentrations for the same watershed, different land use. So kind of keep this in mind. If I have a prairie grass, it's 213 minutes to get to this watershed. I think I was 160 acres. Pastures 75 minutes, row crop 70, and the third acre, depending on if you break it into direct or combine it, is about 50 minutes. So again, you can see how land use impacts it. Well, obviously, the longer the time of concentration, the less peak you're going to have. Now, in the LID world, that's what we're shooting for. We want to keep those long time of concentrations available in the watershed. And so we'll kind of look at how we do that. And again, the concept is if we can keep it up in the watershed in the model, we don't have to get to the end where the green infrastructure is. So again, a lot of times within this is probably a little long now, it's kind of old, but the first 300 feet makes a huge difference in the peak flow. How does that water start in my watershed? Well, if it starts in a tall grass and prairie, it's pretty minimal how much flow will peak off that for this 10 acres. If it's my backyard, it's not too bad, but it's a little higher. And obviously, if it's concrete, it just flies up. So again, when you're looking at this from a design standpoint, what can I do in the watershed to try to keep as much water up there in the watershed before I start? And again, a lot of times in the end, in any urban system, we still have to get it out of the system. So again, how much of an impact does that last piece have on it? So if we can keep a grass channel at the end versus, say, a pipe, it has not a huge impact, but it does have an impact. So again, in the LID world, what we do with the drainage system is critical. And again, slope. So again, when you're looking at stuff, how I lay out my homes and houses and grade it, the flatter that first piece of water is, the better. And again, the other thing I like to point out is that if we do build a channel, sometimes it's better if you can to put in drop structures. Because a lot of times with steep slopes, what we're finding out, especially I know in Iowa and Nebraska, is that there's a significant erosion as urbanization occurs and cutting. So our solution a lot of times is just to riprap it. Well, kind of the concept we've come up, it's almost zero slope to be stable in most cases if you can, and you can get some grass established. But again, if you're trying to increase the time of concentration, sometimes the concept of more of a natural channel with drops actually fits better to that LID than just riprapping a big long channel. So again, what's the key points in all of this? Review existing drainage patterns and try to reproduce. Lay out the site to provide longer water travel times, flat slopes, longer flat use drops, minimize pipe flows, more backyard flow channels, and landscape to use tall grasses. So again, kind of some common sense stuff. And again, from a maintenance resiliency standpoint, LIDs greatly impacts the end of the watershed green infrastructure. So what I'm trying to emphasize, even though we're talking about maintenance and modeling, a lot of the modeling you can use up in the watershed to help reduce that final maintenance at the end. So real quick, I want to talk a little bit about some models, just kind of touch on them. I kind of, after putting this together, realized that in order for me to talk about models, it's probably a class in itself or discussion all alone on each one of these. So I just want to touch a little bit about the differences of these models. So again, it's just a general overview. So let's talk about the EPA SWIM model. Again, it's a free model, and it was developed back in the late 60s, early 70s, and basically it was built as a high-level hydraulic modeling for combined sewer systems. So that's kind of how it was set up. And then since that time, everybody kind of liked it, but it was really hard to use. So other vendors have picked it up, and they basically created that original engine, but made it look prettier. And I kind of point this out with the new personal computer systems, computation, which took hours and cost big bucks, now take minutes. And kind of how I know this, like I said, I did my master's thesis on the EPA SWIM model. And to run the high-level hydraulics, I had to do at night on the Iowa State computers. And it was like $500 or $600 for like a half an hour or 10 minutes of run time, which now can fly through your PC. So it's a whole different world, and that's what's made something like the EPA SWIM model a very interesting and powerful tool. And again, I'm not going to touch too much on this, but the challenges with the SWIM model, especially the free EPA one, is that the hydrology is not TR55, it's not NRCS, it's the kind of the sheet flow concept. So again, that becomes kind of that challenge in using that model if you're not familiar with it. And good or bad, sometimes I've had the concept, if I really need to use the hydraulics in the EPA SWIM model, you can do some of the hydrology in a different method and bring it in, or you can kind of calibrate the subcatchment inputs to the some known flows. And again, the model is set up as a calibration model, so it's really geared towards that. And again, they have sub areas, but what's nice about it, it does look at indirect and direct impervious areas. So that's a really powerful tool that's right in the model. It's just, like I said, the hydrology is a little bit unfamiliar. So you kind of have to know how it works. But what's kind of interesting is, I'm going to jump to this next slide, is that had a chance at Urban Drainage in Denver. As actually what they've done is they have the CUHP is the Colorado Urban Hydrology Program, and that's been around actually since I was in college at UNL. But what they've done, which is really kind of interesting, is they've actually created a spreadsheet using their hydrology that's linked directly to the EPA SWIM model, so that it generates the hydrographs in the spreadsheet, and then it puts the flows out there. Then you can use the EPA SWIM model. So that kind of concept is pretty powerful in situations where I like what the EPA SWIM model does, but I don't like the hydrology. So that's kind of how they overcame that. So it's kind of an interesting perspective. And again, all of that's information is essentially free. So it's a very cost-effective way to do it. And again, just to kind of conclude, what like a lot of models are doing, including SWIM, is they're basically incorporating LID into their models directly. So EPA SWIM does have an LID component, but I kind of looked at what the challenge is, because the original EPA SWIM model was a load model for pollutants, so they kind of incorporate that into their LID also. So they kind of look at, well, what kind of bad boy pollutants are coming off your watershed, and how does the LID deal with it? So it's a relatively complex process where, for the most part, a lot of the water quality and green infrastructure design is pretty straightforward. It's a water quality volume, and you just plug and chug. So, but again, if you're looking at watershed impacts and big pictures, it might be something to consider. And again, that's kind of the LID, but pollutant load, and that's kind of repeating myself. Again, real quick, I want to jump HEC HMS. This is right out of their manual, but again, it says it's for small urban watersheds and future urbanization impacts. Again, the only reason I kind of threw HEC HMS up here is that it's a free model. And so it's designed for larger watersheds, but it says it can be used for smaller ones. It has lots of options, which is because it's a core model. Have to do a lot of the complex hydraulics outside the program, which kind of makes it a challenge. There is a GIS component, and I think you can use this if you learn it for simple GI projects and you kind of repeat the process over and over. It'd be a very powerful tool. It wouldn't cost you anything to do. It doesn't have the LID built into it, but you can do the direct impervious. And again, the highlight of it, it's free. So again, if you're looking for something similar to TR55, which is in the Iowa stormwater, and you want to do some modeling and you don't want to purchase any software, you can dive into the HEC HMS world and make it work for you. And again, I'm going to talk a little bit, include this by the proprietary programs. And again, like HydroCAD, which I'm going to talk a lot about here at the end of this presentation. But again, they're more user-friendly. They got a quicker learning curve, tend to be more up-to-date with current trends. Support can be doing much better, required by local governments, and improve on the methods. The cautions are, I think they become very black box, which makes them easy to use, but can easily cause some problems. You can have unqualified modelers doing the modeling. Cost creep, a lot of times you buy it, and then all of a sudden you find out it costs a fortune to maintain it. And again, there's lots of add-ons to the program, but then they may create other problems. And XP Swim is one that kind of comes to mind, where they added the TR55 into the program, so it generates the hydrographs, and so all of a sudden you're using a very expensive program to do something you could probably do for a lot cheaper. So real quick, I'm going to talk a little bit about modeling various BMPs in the Iowa Stormwater Manual. I just want to kind of touch on this to give you the concept that everything I'm talking about here at the end in the case study can be used to do anything that's in the Iowa Stormwater Manual. And again, the design process is very similar to the hydrology book. It starts out in the planning stage, looks up in the watershed and the LIDs, and then we look at the end of the pipe products at the end. But the challenge with the part of the Iowa system is that when you go through it, it's a lot of manual calculations, and from that standpoint, which is typical of a design manual. But the power is that you're taking that information and putting in a model, say like HydroCAD is, I literally can hit one button and I can get 15 storm events in no time. So what it tends to do when you're looking at the resiliency and maintenance of your system, if you have to do a lot of manual calculations and you go through iterations, you kind of don't get to that point where the what ifs kind of die on you. So again, that last one if, that what if you don't look at it, might be the one that causes your system to fail. And real quick, really all GIs can be detention ponds when you really think about it. So you have an inflow coming in, some water depth occurs, you lose some through the ground at the bottom, you might lose some that sits in your system and goes up through the atmosphere. So a lot of times you'll put an under drain in if you don't think you're getting enough losses through the soils. Usually have some kind of controlled outflow, and then a lot of times you have an uncontrolled outflow. In other words, big event comes, where does it all go? So if that's the basic concept, they can all be modeled. So let's look at a couple of examples that maybe you think, well, those can't be modeled, but can they? How about a green roof? Well, think about it. When it rains on the roof, it gets some kind of depth. You're designing it to obviously take some kind of losses in the soils, and from that standpoint, it has a controlled outlet. Usually that would probably be your gutter system and emergency overflow right on the roof. And if the system jumps over the edge of the roof, you basically have an uncontrolled outflow. Well, you can model all that on a roof as a detention pond. Same thing with a pavement system. Again, some depth of water will occur on your porous pavement. You're going to lose some of it, which is your design. All the excess will probably design a gutter for it to flow down and leave the system. And again, if you get way too much water, it's going to go somewhere. So again, these can all be designed in the modeling system as a detention pond. So key maintenance challenge, we're going to discuss, now we're going to really jump into the whole, how does modeling fit in the maintenance system? So what is the point that we're going to look at when we're looking at maintenance? Well, first of all, we don't want blowouts. Too many BMPs and GIs just blow out. They're way undersized for the amount of water that's getting there, or we didn't look at what would happen when all that water gets out. They blow out, they look terrible, and everybody goes, why are we doing this? Plant survival is another point. Too many times the water sits too long, or you have the wrong plants, they can't survive the BMP. Resiliency, again, can we determine if we do get something, how can it bounce back and how fast? Those are really the three key ingredients that we're going to look at when we're modeling BMPs. And there's others like access, the purpose of it, and sediment buildup are all other maintenance challenges. So let's look at what I want to jump now to is a case study in Spring Lake Park in Omaha that I had an opportunity to work on as part of the CSO project. And what I like about this, and as part of this presentation, it's one thing to talk about modeling, it's another thing to actually do it and see it work. And so this is a great project and that you can actually touch and feel, and it's actually worked very, very well from the modeling standpoint. So where's it located at? It's actually located in South Omaha, and it's just a little bit south of the zoo, if you're familiar with where the zoo is in Omaha. And it's a little bit south of downtown is where the project's at. And like I said, it's part of the CSO project. So really what happened is the project originally was a big gray project for the CSO, where they were going to pipe all the stormwater down to the Missouri River. So there was a lot of discussion early on, could we make this into a green project? So it's a 416-acre watershed. It's about 50-50 between park and residential, and also includes a 9-hole golf course. As part of that initial study when we worked on it, we had 83 potential BMP technologies were identified. So there's lots of things we could do in that watershed. And again, the whole goal was to try to mimic the natural hydrology of that watershed as part of this project. So again, if you're trying to mimic something, you got to model it. So in the end, here's, like I always say, there's lots of green going on. There's 6 extended dry detention basins, which basically are storage areas that will dry in the Omaha definition. Or I mean, extended dry detention are kind of your typical wet dry detention. There's 5 dry detention basins, which will dry out. There's 3 pure infiltration basins. There's 2 wet retention wet ponds that'll stay wet all the time. There's 2 constructed channels that replace pipes. There's 1 constructed wetland, but it has lots of cells. And there's a bioretention or 1 rain garden. In other words, there's lots of future maintenance that we had to deal with. So again, how does the modeling play into looking at that maintenance? This is actually, it probably doesn't show up great on the screen, but this is the complexity of the model that was done. And we did HydroCAD because that was something I was familiar with. And Again, part of the power of HydroCAD I like is the fact you can do a lot of hydraulics in it, different outlet configurations and things like that. So again, it was a pretty complex, very complex model. Each watershed was broken into direct and indirect impervious, like we talked about earlier, to make sure that for the small events we were getting runoff, to the big events working like they were supposed to. And again, the project was actually broken into 2 phases. Phase 1 has now been completed and cleared out, and that's most of the pictures will be from that. Phase 2, they're building as we speak. And then downstream, there really was no green infrastructure, so it's a pure gray system. So really, part of the whole project was, and I've seen too many times, was how do we design something to prevent blowouts? So the whole system and the modeling was geared towards that, a lot of that towards that concept of this. And too many times you have that, when you just look at it, you can say, well, I hate to say it, but duh, you know, where you look at it and say, that's kind of that common sense. You would never put a small rain garden with a great big 36-inch pipe, but it sends people do that. Again, I'll kind of skip over this. So, whoops. So there's really 2 ways to prevent the blowouts, and we actually had both of these on this project. An example is a first flush diversion. So you can do that in a manhole, like you see on the left here on this picture, which basically we have a low pipe and then an overflow pipe higher in the manhole, where the low pipe goes to the BMP and the high bypasses. So we're only taking that first flush and putting it in the green infrastructure BMP. And then the curb cuts is a pretty common way to do this. And we actually don't have any curb cuts on the Spring Lake project, but I wanted to at least talk about them and show that they are part of that whole first flush diversion concept. And then the other one is overflow structures, which are actually built right in the within the BMP. So again, there's several examples of those, and a couple of those are actually in Iowa. And the one on the left, I kind of like these cones that we used on Spring Lake, because they keep the trash, doesn't necessarily block them. They don't look too bad. So what did the model look like? So this is, I'm just going to talk about how you model a first flush, again, from a maintenance standpoint. So again, the maintenance component of a first flush is, if we can keep the high flows out of the BMP, we won't blow it out. So how do we model that? So we start at the upper end, and like I said, we compute the drainage area. That's where we break it into direct and indirect from the watershed standpoint, and then recombine them. Well, that comes into the first flush diversion manhole, and then the drop. This is, in this case, we just had a drop manhole to reduce velocity. So the first flush goes into the drop manhole and heads to the BMP, which is located here in the model. And then anything that bypasses in the manhole where the number 2 is located at, that then goes back into the main storm sewer line. And then anything come out of the BMP gets back also and joins that and goes back in the main storm line. So that's kind of how the bypass first flush diversion works. So now, how do you actually model that? I mean, that's a cool picture, but let's look at the actual model and the results of that. So again, inflow comes into the first flush. All rainfall then is, the way it was designed is that actually for 1 inch. So anything 1 inch or less gets diverted into the BMP. And then anything in excess of that 1 inch goes both into the BMP and then bypasses, which then goes down line. This is off the plan sheet, obviously. And then anything gets in the BMP will head into the control structure, and it flows back into the main conveyance line. And then if all heck breaks loose, we have to look at how will it blow out and go over the top of the overflow. So here's what the HydroCAD model actually looks like on the left. So we start with, in this case, on this sample, we had a 12-inch round pipe at the bottom. So again, in the HydroCAD, we just model it as a culvert in the manhole. And then the next thing is, well, we need to have that bypass located somewhere. Well, the nice thing about the model is you can run the 1 inch and it'll tell you how much water's ponded or stays in that manhole. And then you set the invert for that overflow at the high water mark in the manhole for that first flush 1 inch. So that's how that invert was set. And then you can size that pipe based on that. And then finally, because with, and this is just kind of unique to HydroCAD, is that at some point, it doesn't, if you had a better hydraulic model where surcharge is allowed, you could do a little bit more detail. But in this case, since again, it's kind of a relative model like we talked about, we want it to blow out of the manhole. So basically, we put a primary, that's the top of the casting. So again, this is the example of what the hydraulics look like on the outlet. We just had a 6-inch orifice that's controlled the whole system. And as you can see, even though we had these stand pipes, they were there more to collect trash, not to control flow. So they got lots of holes in them. The actual control then is that 6-inch orifice out of there. Then we have to put in the design overflow. So that's there, and it was like 80 feet. So we make sure we got plenty of distance so we don't get high velocities. And let's really quick, I want to go through how the numbers in the model. So here's the first flush model. So again, we have 1 inch, we have 4 CFS coming into off the watershed. It reaches the diversion manhole, and you can kind of see for that 1 inch, all the flow goes to BMP, none of it's bypassed. It's designed that way, as you can, from that standpoint. Then as it reaches the BMP, so we have 4 CFS reaching the BMP and 1.4 leaves it, and it gives us a high water elevation. So everything is good. We want some detention. And then in this case, none of it will overtop because it's all going to go through the pipe and it heads down. Now, the power of the model is now we said, well, let's look at the 10-year. So again, we have a lot of flow coming through, 43 CFS, but it hits the diversion manhole. So instead of trying to run all 43 CFS through the BMP, we're only running 13 CFS through the BMP, and 34 of it's going to bypass. So that's kind of the power of how this works. And again, I just realized the math didn't work, but I must have typed in a number wrong. Anyway, so from that standpoint, we get the bypass. This is what hits the BMP, 13 inflows. There really is no detention now as we get the higher flows, because the pond really isn't designed for detention at anything greater than that 1 inch, but it does tell you how high the water is. And again, in this case, there might be a little bit of overflow and also going back into the system. And then again, well, if we want to build it from a maintenance standpoint, let's check the 100 year. We'll fly through here. And again, the same flows come through, and we can kind of see how it all functions. Again, the flows are going up. But what I want to highlight here is part of this whole design, what the power of the model is that from the standpoint, oops, didn't. What I want to highlight, here's that velocity. So again, it's the velocity over the weir, but that's actually the overflow. Now, if you're building from a maintenance standpoint, you don't want to blow out. 1.0 CFS and 1.3 feet per second velocity is pretty maintainable with a grass area. And again, that's the power of the model. When I begin to run different events, I can actually see, well, am I going to lose that berm where these red arrows are? And if you kind of look at the picture at the bottom, it kind of shows you it's a natural grass area and it's been very well established. So I'm pretty confident over time that even if I do get some huge rainfall, that is going to remain in place. And again, here's another first flush structure where we actually put a weir inside a manhole, and you can kind of see how that diverts it. Part of it goes to BMP, it jumps over the weir, and it just continues on its merry way downstream. And real quick, I want to touch on how you do a curb cut. This wasn't in Spring Lake Park, but again, you can design it as kind of this system where it's a street cross section, and you can do the curb cut as an orifice. But the challenge is with the bypass is, well, how deep does the water get before it bypasses? Well, what you can do, if you look at inlet capture, at what point does the water 100% get intercepted? There'll be a depth in the street, and you could kind of cheat that system and make that work. So it's doable. And again, here's kind of, I'm going to kind of time, because we're running the time, I want to make sure I get through all this stuff. And again, why is this important to look at possibly curb cuts and model it? Well, let's say we run 100 year on a curb cut and we get 3.8 going to GI and 5.6 bypassing. Well, here's what I've seen too many times on these curb cuts is, well, the stuff I put downstream in the curb cut gets blown out or eroded. Well, the nice thing is if you model it, you can look here. In this case, it's 3.8 feet per second of velocity coming through that orifice. That's quite a bit of velocity. So it's going to take a little thought on how that is going to be stabilized at that point. So again, it helps with that maintenance, helps with that design. And the next thing I want to jump back to Spring Lake Park, but again, here's another case where we can use GI and model it to make sure it's going to work. Well, we had a problem. We had 600 or 800 feet of pipe that we were going to have to put over this big steep bank, and it was already badly eroding through this channel. We had about a 70-foot drop from the top to the bottom, and we had to somehow run a pipe through all of this. So we thought, hey, is there a green infrastructure solution to get rid of all this pipe? Well, of course, the answer was yes, an infiltration basin. But the challenge was, how do we design it to make sure it's going to work? Well, that's where the model comes into play. And again, I want to note these rocks that are in this infiltration basin. That wasn't necessarily what it's designed for, but it's kind of interesting. After they went in, we kind of liked the fact that they're a little bit bigger fieldstone rocks, and this kind of makes it almost a little bit better infiltration basin. So again, the challenge with an infiltration basin, you don't want all the junk to get in there, the sediment and all that. You want to keep it as clean. So we had to put in a pre-treatment BMP. Again, we'll talk a little bit about that. This is the other case where we have an overflow structure for the BMP. And again, we have a standpipe, and then we have the overflow structure because we couldn't really bypass it in this one. We wanted it all to go through the BMP because there's basically no place to bypass it except into the infiltration basin. Again, we want to make sure we captured it all. So again, here's how you kind of model that concept. You have the standpipe with its outlet. And then you look at how do you set the invert for this overflow structure? Well, in this case, we run the model. We say, well, how deep does the 1 inch get? Well, let's set the invert of this casting at the 1 inch, so then it begins to overtop. And then we look at the outlet pipe is actually now a control structure from this system, which is part of the design. And then finally, we still have to look at that overflow. How does that function? So again, we have a big broad-crested weir overflow. And when you're looking at the different flow events, we go back to that whole concept of velocity and overflow and how we can model that. So again, it works really well. It actually is one of the best working facilities we have out there. But what I really want to point out in this design, as we designed it in the model I call an exfiltration outlet with a 40-foot overflow weir, is the fact that what we were really looking at was those velocities of the overflow out of that infiltration basin. And if you kind of look for a 1 inch, we get 100% capture for the storm. So again, from water quality standpoint, it all sits in there. But as we get to the 10 year and the 100 year, which is basically our conveyance system, we have really low velocities leaving that, coming out of the infiltration as part of that overflow. And how did we accomplish that? Well, the way we accomplished that is we started putting in a lot of these concrete ribbons to make sure we get a constant overflow out of that basin. Then we don't get those little rills and information, rills developing through that berm. And again, that's part of that modeling. We said, well, if we get a constant weir, we know we're going to have a very stable maintenance system over time. And again, it's a pretty inexpensive maintenance process. Again, here's what it kind of looks like. It's very vegetated. And again, we're pretty confident at over time that we will not have any problems if we do get high flows. And again, this is kind of a grass area, and it looks pretty good from that standpoint. So I got to kind of go through these. I got a lot of stuff to go through. We'll kind of fly through these, unfortunately. Again, how do we model debris and trash? We can look at it from the standpoint of, we've had the problem on this project with the trash. And what we can do in the model then is we can basically have a different starting elevation for sediment buildup, which is really interesting. And then what this model has is really say, well, what if our outlet's plugged by 50%? Again, we can do a trash what if through this model. Next thing is we did a green infrastructure channel as part of this project. And again, the pond and the channel replaced over 600 feet of storm sewer pipe and LID perspective that increased the travel time. And again, we had designed this for a 2, a 10, and a 100U. So again, here's the piece of the model. We did put a detention pond upstream to make sure we can keep the channel stable. That, again, is in the model. Then we had the downstream channel. This is kind of what the model looked like. We could use the HydroCAD for the low flow. We put in a HEC-RAS. And again, we used HydroCAD for the high. So again, what we're trying to do here is reproduce a floodplain with low flow, high flow. And we actually had to put some drop structures in. Again, the power of the modeling, I'm modeling everything from a water quality event all the way up to the 100U. And here's kind of those systems. And it looks pretty dang good. It's actually turned out to look like a revised or remodeled floodplain. The other thing is, in a case where our modeling shows we have an emergency overflow, we got to make it resilient. So again, here's a case where we had a detention pond. This was our emergency overflow. We kind of used a lot of Fleximat on this because the advantage is in a green infrastructure environment, you don't want to see concrete. So again, here's on the left, you can see what it looked like before we built it. And then it's fully vegetated now and ready for that big storm. And we had some constructed wetlands. Again, the key in those is we had 4 wetlands is what plants to put in. And in this case, what do we do with the model? We're really looking at drawdown time. How wet were these plants and will they survive? Well, the key is also we're good at hydrologists and hydraulics, but we're not that good. So one of the things we did put on the outlet of the wetland was a stop log structure so we can adjust the elevation of the wetlands. Then if we have the model set up, we can see what the potential impacts are of that in the future and really calibrate it. We also put in gates again to add some maintenance to it to make sure that everything's okay, and we got some adjustments. The other thing is when we're doing the modeling, the nice thing about doing modeling to this level, we had to look at all the outlet velocities from all the systems. And again, you can kind of see the table up above. But again, we're trying to reduce maintenance costs. And again, we use a lot of Fleximat in the green infrastructure world because it's so hard when you go back and do maintenance with a backhoe to try to work around riprap. The nice thing about a Fleximat or a flat product like this is you can literally just scrape right over the top of it carefully. And again, here's kind of the velocities. And one more last example of power modeling. We actually had a design where we had an overflow design for just under the 10-year, but then it kept washing out. We checked the model. It turned out they actually built the casting a little bit too high. And when we redid the model for what the actual casting was, we found out, well, that's why it's overtopping. They actually reduced the casting, and we haven't had any problems since. Like I said, we do have one rain garden. Probably could have designed a little bit more of a bypass. And I like this. How do you model for a truck to hit your rain garden? Obviously, you can't. But it's a great quote from a local resident that worked on the project. Some idiot messed up our park. The bumper piece and shiny chrome plastic pieces all over the place looked like it came off a newer black pickup or maybe an SUV. So again, neighbors watching out is really good. Real quick, this is the outlet from the whole system. It's a very complex model. It has 1, 2, 3, 4, 5, 6, 7, 8 different outlet configurations to make this work. It actually turned out as part of this project, the street was a dam, so we had to actually do a dam analysis. So again, by setting up the model, not only from the green infrastructure to the 100-year, we actually did the dam analysis in the green infrastructure model. And I'm going to skip over these. Real quick, concept of green infrastructure treatment train. There's lots of stuff. There's a series of this in the green infrastructure project. I came up with this low impact conveyance train. When water hits your roof, it has to leave. And again, sorry to make a fly through that. And real quick, so we have a little bit of time for questions. Again, why should I model? Well, will this be a highly visible project? So failure could set a green infrastructure program back years. I found that to be the case a lot of times. When these things fail, then the politicians begin to question why you're spending money. So I think the power of the modeling is you can really get a very stable system, like I showed in a lot of these examples. And then also for a conveyance of 10 years, failure acceptable and repair the system expected. Again, you're incorporating into the green infrastructure that whole gamut of design, from the water quality to the conveyance system as you're looking at it. And again, if failure is not acceptable, it's not in your streets. Most of the time, it's not in your storm sewer pipes. It probably isn't acceptable for your LID green infrastructure system. And again, large storm events. Can you watch it blow out and be happy with it? Too many times we're studying green infrastructure. We're not designing green infrastructure. So again, the nice thing about the modeling, it does allow us to really do a design component of it. And again, some other key components, is it part of a protection downstream? What kind of plants you're putting in? If you don't care if your plants survive or don't survive, it's less critical. But man, if you're spending a lot of money on plants, probably work with the hydrologist to make sure they're actually going to survive. And then again, if you don't have any money for maintenance, you better make sure it's pretty maintenance free at the end. And that's kind of where this modeling can come into play, and you can design components that keep the maintenance from that standpoint. Real quick, if you're ever in Omaha, this is my contact information that's available. Love to give you a tour of the site. It's a really neat site, and when phase 2, it's even going to be better. But like I said, there's 22 BMPs within a park, and you don't get that very often in one site. And finally, that's it. So I left only 7 minutes for questions, so I apologize for that. But
no, that's okay. And actually, thanks, Rocky. And actually, I don't see any questions coming through on chat. So
okay.
If you have anything, if you skipped anything you want to go back to quick, we'll stick around and see if we have any questions. Otherwise, excellent presentation. Thank you so much for sharing with us today. For participants still around, if you're looking to get PDHs for today, just type your name into the chat box before you leave. I'll stick around for 10 minutes or so just to make sure you're wanting to do that. You had time. Otherwise, email me with further questions. And then Rocky's contact information is on there as well.
Yeah.
So yeah, go ahead, Rocky.
Well, I think the only thing I kind of skipped over, the green infrastructure treatment train is kind of my fun little thing out of this, but it's really interesting in this project is that actually when we were designing it, trash became an issue. So the SAFL baffles, if you're familiar, but it's kind of this trash. So there's actually trash collection up in the watershed at the actual catch basin. So it's when it rains in that watershed, first the trash gets picked up, then it comes down into the watershed and it goes through some of those first flush diversion structures and BMPs that we talked about. And then after it goes through those, it goes through the down through that meandering channel I talked about. It goes into some constructed wetlands. Then it goes into the actual lake, which is Spring Lake, and we have another channel. And then it finally hits the pipes before it gets to the Missouri River. But I think, and I don't have it on the slide, but it's almost like 3,000 feet of pipe that we took out of this project through green infrastructure. So that's why, from the standpoint, if you're ever in South Omaha or want to look at the map, you can walk around. It's not like it's locked up, but it is a really good example of how you can use green infrastructure and LID on a large scale, but there's actually a lot of small scale stuff there that fits. And I also kind of like throwing my LID conveyance train. Sometimes we really don't think about how, when water hits a roof, where does it go? And if we kind of follow that flow path, kind of the quote time of concentration in my LID, and then just look at, well, how am I hitting it each time, and what am I doing with it? So again, in looking through the Iowa Stormwater Manual, there's lots of good stuff in there, and just kind of follow that and convert it into the modeling world is a good approach, I think. So
excellent. All right, well, we'll stick around for a few minutes here. Again, if you want PDHs, type your name into the chat, and otherwise, thank you, everyone. I'll close down the webinar here in about 5 or 6 minutes. Thank you. And thanks, Rocky.
Yeah, like I said, my contact's there. Feel free to call me, and if you got any questions, I'm the nice thing about having my own business, I have time to do that stuff. So I love to talk about it. So, and help anybody out that I can.